Okay, so for this lecture, we're going to discuss the embedded simulation of dynamic systems. So we've been talking a lot in the last few weeks about control systems, kind of a high level, looking at how we have dynamic systems that are described by differential equations and the different ways to represent those. Well, how do we actually simulate that in an embedded control system? Um, or implement a controller, for a dynamic system in an embedded control system. And really, it comes down to the fact that everything we're doing is in relation to time, in the microcontroller. So we have to have a consistent time base, a kind of a delta t, if you will. And we have to be careful in estimating, differentials of signals because, as we talked about in class, anytime you estimate a differential, you're using past values of an output, kind of doing drawing a linear slope through those points. And if your dynamic system is changing very quickly, sometimes those previous values, the slope through, 2 points in the past, may not be a real good estimate of what the current differential is. That's why we typically do things in state space. So when we estimate an integral, if you're estimating an integral up to your current point, it's really a sum of all those previous elements. So if you're slightly off in time from where you're calculating that, it's really a very, very small delta from that actual value. So all that being said, it's a lot easier and more accurate to approximate integrals that are, of a variable that's changing in time as opposed to trying to calculate the differential of a variable that's changing in time. So today we're going to talk about, you know, how we actually implement that in code, forming the state space equations in code, and then we'll go through a programming example where we will basically implement a second order system, simulate that in code, and use a real-time serial plotter to take data from the microcontroller that's being output on the UART and plot that on the screen so we can kind of see the real-time response. Okay. So we've looked at this before. This is kind of a system block diagram of our motor and driver and control system, right? So this is kind of ultimately where we're going to end up if we want to design a control system that's going to have the motor reach a commanded RPM. So in this case here we have our RPM command. D of S is our controller, some kind of a control system. It's going to be commanding some PWM duty cycle, so essentially a value from 0 to 100% to this motor and driver. You should be starting on deriving the parameters for this motor and driver. I think that was that T sub K sub M and T sub G, if I'm not incorrect. Then we talked about how that gives us some physical RPM response, and we're using the encoder to measure that RPM, and we really kind of write our sensing code in the microcontroller such that the output of that is calculated RPM. So that essentially makes this H of S block equal to 1, right? So we have RPMs at the output, we have RPMs coming into this difference block. So really this does end up being an RPM error, and this having this H of S equal to 1 is going to simplify our transfer function, so we don't have to have extra complexity there. And then of course we want to just output to the PC console through our USART. We want to output what is that calculated or measured RPM, if you will, so we can kind of see what the actual response of that motor is. So in this case, we don't have an actual motor, so we will just kind of simulate an overall transfer function, the combined transfer function of this entire system, right? The feedback system of the controller and the motor and driver is ultimately what we're trying to do. Okay. Okay, so in order to design a control system to command this motor and driver to our desired RPM, we need to understand the entire transfer function. So it's really it's a combination of a lot of different elements, right? When you're talking about using a microcontroller to generate pulses, which goes to a driver, which translates that to a drive voltage, which goes to the motor, which has its own type of response. There's really a lot of elements to this, right? So we can kind of break it down into pieces or blocks. If you start with the motor and driver, really we want the output of that to be angular velocity, which is radians per second. We don't really care too much about theta itself. We're not trying to command the motor to a very specific position in theta, right? We're trying to command it to a particular angular velocity. So the output of the motor is some angular velocity. The input is going to be some kind of a drive current given by the driver. The driver is going to accept a PWM duty cycle. So really that's kind of the only parameter there. Between those blocks we care about is what's the actual percentage duty cycle. That's going to be created by timer 2, right? So it's going to have a duty cycle per pulse ratio, right? So we're going to give it a pulse value. This is not a physical pulse. Remember, this is the pulse value in programming the timer. So this would be a number of counts, so that if our ARR is 10,000 in this case, this would be the number of pulses out of those 10,000, the number of counts where the duty cycle is on. So and then that's going to be driven by the calculation of RPMs per pulse, and then obviously back to an RPM command. So if RPM command, this is going to give us actually pulse per RPM, if you will. That's going to give us the pulse value, which is going to give us a duty cycle, which will drive the driver to a certain drive current, which will make the motor turn at a particular angular velocity. So you kind of see the whole chain of what we're trying to do here. And really, one of the keys about dynamic systems is we don't really care about what some of these specifics are. We don't really care what this duty cycle is, or what this drive current is, or what this pulse count is. Those are irrelevant to us, right? I don't care if the duty cycle ends up being 20 or 50 or 70. All I know is I really just care about this angular velocity. So we don't need to know all the internal specifics of these parameters. We just really want to know, what's the transfer function from the PWM duty cycle, to this motor angular velocity when we're trying to describe our actual system here, right? So the motor and driver together, we really just want to know, for a particular PWM duty cycle, what is this, or a step in this duty cycle, what is this, what is the response of the motor and driver to that? Okay, so we looked at the motor and driver transfer function before in the DC motor modeling, and we saw that this is really just kind of a first order system, and ends up having a step response that looks like this, where we have the angular velocity of the motor is some constant kg times this 1 minus e to the minus 2 over tm. So kind of a final value and dynamic exponential response, which is typical of a first order system. So we can write a microcontroller application to apply a 50%, actually that's going to be a 100% duty cycle. These charts are old. Let me change these out real quick. Okay, I'd made some corrections to the DC motor modeling slides that weren't updated in here. But essentially we're going to write a microcontroller application to apply 100% duty cycle and record the motor speed over time. So if we want to simulate this response in the microcontroller, we want to basically look at the step response of that. Okay, and that's what we did for the motor modeling assignment. We recorded the step response of the actual physical motor, and that can be used to determine these two parameters that describe our driver and motor system, right? So you should be kind of working on that right now. Once we have these values, then we know our motor and driver transfer function G of S. Okay, so we looked at the measured response, kind of messy, noisy, and we can find values kg and tm that give us this response. Okay, so now once we know the motor and driver, we have this piece of the entire system. So one block of our overall closed loop transfer function. So now we can design our timer and RPM calculation so that this h of s is equal to 1. It's pretty easy, right? Because we know how to do that. We know how to interpret this encoder from a motor and, translate that to actual RPMs. Okay, and since we don't have a lab here and we're not using actual hardware, we need to basically simulate this motor and driver in the microcontroller. So that's really what we're going to focus on today, is how do you actually simulate a dynamic system in real time, with some sort of a known transfer function. Okay, so in this case we have the motor and driver given by this transfer function. We have some kind of a time-based input, could be a step function, could be anything, and we have some time-based output for that. So how do we simulate that? Okay, well the first thing you might think about is, well, let's just, take the inverse Laplace transform of that, and, we basically get a differential equation that looks like this, right? For a, we get tau times some y dot plus y equals u. That's a typical first order response, right? Well, you may think that you should try to approximate that y dot, right? That y dot of t as, y2 minus y1 over t2 minus 1. So you might have some, some previous outputs. You're going to look at basically the slope of the output, at a particular time in the past. But as we've talked about, and as I've alluded to, that really does not work. Now, I say this does not work if your system is changing very, very slowly compared to your time base. This can work, but once you start getting into systems that change relatively quickly compared to your time base, this really starts to fall apart. So it's not always reliable, so I would hesitate to use this method in embedded control systems at all, just because it's it can cause issues. And basically, if you think about it, if we're looking at a system that's changing quickly, we're trying to look at the current derivative or slope, and we're using past values. You can see how estimating that slope, could be inaccurate. Okay. So the best approach is to use state space representation. So the reason we talked about state space in previous lecture was because that's really how we're going to implement a dynamic system in the microcontroller. In this case, we're estimating integrals of variables instead of derivatives of variables. And estimating integrals, as you know, is much more well behaved. We have a big sum over all of time. We're adding one more value, to our sum. So it lends itself to being a lot more accurate for rapidly changing systems, because the small errors don't really, a small error doesn't cause a huge change in our estimation. So let's use a second order transfer function kind of as an example. We'll go through the method for how to implement this in an embedded controller, embedded system, and then we'll actually go through a little bit of a programming example. I'll show a little bit of code on the screen here in these slides, but we'll go through and actually code this up so you guys can see how to actually implement this. And at the very end, I'll have an assignment where you guys can kind of repeat this, but for just the motor and driver, so you can simulate the step response of the motor and driver. Okay, so we're going to use a general second order transfer function. So here we have y of s over u of s, or h of s for the closed loop system is going to be, in our general second order form, right? So here we have our omega n squared and our zeta, so our two parameters that kind of describe this second order response. Depending on these values, this could have, the roots could be complex conjugate roots, or it could be a dual root, could be real roots. In this case, we'll pick some example values that'll give us some sort of response when we actually code this up. But if we look at the inverse Laplace transform of this transfer function, we get this actual differential equation. Second derivative of y plus 2 zeta omega n times the first derivative of y plus omega n squared times y is equal to this omega n squared of our input time function. Okay. All right. So really, we're going to put this into state space form so we can define state variables. This is a second order system, so we need two state space variables, x1 and x2. X1 will be equal to y of t, and that's really kind of what we're interested in, right, as our actual output. This is going to be, in this case, the output of our system will be the speed of the motor, right? So this isn't theta, this is actually, I believe, theta dot because of the way we've written our transfer function. So x2 will be the derivative of that, essentially theta double dot. Okay, so in state variable form, we have x1 of dot. So here's our original state space variables on the right, just for your reference. So x1 dot is going to be equal to x2, right? So we want all these state space derivatives in terms of other state space variables or the input. And then x2 dot is going to be y double dot, which if you look up here in the original equation, you can see that's going to be this. So that x2 dot will be equal to, you know, all this stuff over here on the right side. So that equals, you know, minus wn squared times x1, and then minus 2 zeta omega n times x2, and then plus omega n squared of u. So now we have the derivatives of our state space variables in terms of, you know, our transfer function parameters and the state space variables themselves. Okay, so very key there. We want all these in our state space form. We want to express the system, you know, in terms of the derivative of our state space variables equal to, you know, all the state space variables and the input. Okay, so really, if we want to estimate these state space variables, x1 dot and x2 dot, if we want to estimate x1 and x2, these are derivatives, right? So we just need to integrate those. So x1 it will be equal to the integral from 0 to the current time of x2 of tau, right? So x1 dot is x2, so x1 will be equal to the integral of this x2, okay? So we're really just integrating our x2 variable from 0 to the current time. So we're summing up all the previous values of x2 that we've had. So very easy, nice estimation, where if x2 is misbehaved, has some really fast transitions, or even non-linearities, if you will, you know, this integral really kind of smooths that out and makes this x1 state variable nice and predictable, right? Likewise, x2 is going to be the integral of what's over on the right-hand side for the second equation. So basically, again, we have the integral, or summing up, of all these previous values of our state variables. Okay. All right, so you can kind of see we can go through an iterative process here. And for each step, each time step, if you will, in our program, we're going to have previous state variables, x1 and x2, that we previously calculated, and we can use those to calculate the new state variables using these integral estimates. Okay, so kind of written that up here. There's, you know, several ways to approximate integrals, but the easiest is really just kind of the definition of an integral. If we have a previous point and we have a slope, you know, we have a slope and a delta t, then the new value of a function, right, is going to be the previous value, and then we're going to have this dy dt times this change in time, right? So the slope times the amount of time, that's going to give us the new value. Okay, so in this case, if you kind of reverse that, you can say that y of t in this case is equal to the integral of the slope of that function, right? But now we have to kind of include that initial condition. So we have y of t in this case is approximately equal to our previous value of y plus that delta t times the slope, which is going to be the y dot. Okay. All right. So in this case, for a state variable, x1, you can kind of think of that as this value, is going to be approximately equal to the previous value of that state, which would be this dot down here, plus our time step times that previous value, t minus delta t. Okay, x2, t minus delta t, where x2, remember, is the actual slope. Okay, x2 is the slope of our original state variable. Okay, so that's really how we're going to create, using a discrete system, how we're going to estimate these state variables. So now we're looking at kind of estimating an integral, which is much more behaved than, you know, trying to estimate derivatives. Okay. So in this case, our previous state variables, you know, x1 is now kind of equivalent in this case to our previous y, and x2 is going to be our previous y dot. Okay. Okay, and if we want to estimate the value of x2, we have our previous value of x2 plus our delta t times our previous, right, or our slope, basically, right? So delta t times our slope, and our slope is given by this, right, which is our x2 value. Remember, our x2 is equal to the slope of x1, right? Okay, so this is kind of our integral estimation. All right, so hopefully that makes sense. This is basically our two equations that we're going to implement in the microcontroller. So we have x1 is equal to the previous value of x1 plus delta t times the previous value of x2, which is the slope. x2 is going to be our y dot, which is equal to our previous y dot plus this delta t times our y double dot, right? The slope of y dot. And our y double dot is going to be equal to this, right? Yeah. So hopefully that makes sense. It's, you know, you got to think through it a couple times sometimes to kind of keep track of what are the actual parameters and what are just state variable values. So just remember that x2 in this case is y dot. So we're basically saying y dot is equal to the previous y dot plus delta t times y double dot. Okay, so two equations here, and now, you know, we're dealing with things that are discrete values that we can all implement in a microcontroller. Here we have previous values of x1, so we're dealing in terms of delta t, which is, you know, a consistent time base in our microcontroller. So we know what delta t is. So we're looking at each state variable being a function of previous values plus some delta t, which is consistent, you know, times some other previous values of other states. So we can simulate this easily, and it will be well behaved, you know, as opposed to trying to approximate derivatives. So x1 of t minus delta t is the previous value of state variable x1. x2 of t minus delta t is the previous value of state variable x2. So we're kind of updating the state variables given the known derivatives of those state variables as functions of our transfer function, right? And then, so we're kind of keeping an updated sum or an estimated integral of those variables. Okay, so if we have a consistent time base, delta t, we can update those state variables according to these equations above, right? So we can calculate x1 and x2 iteratively based on previous values of x1 and x2 if we have a consistent time base. So notice that's kind of a key here, is that we really need to have a consistent time base. And I think we know how to do that, right? We've talked a lot about timers. And if you think about kind of implementing this updating inside of a callback function, we can, you know, set up a basic timer that will trigger at a consistent time. And every time that callback function is issued, we can update these state variables. So that is one element of how we can simulate this in an embedded control system. Okay, so let's say we want to simulate the response of this second order system to a square wave input. So we're going to basically be getting a square wave as an input, and we want to see how this system responds. So this is the strategy of how we're going to actually implement this in the embedded code. So we're going to use timers and interrupts so we can accurately predict how often things are going to happen. So in this case, we'll use a basic timer 6 just to create an input signal. So you could have a signal coming from the outside world if you wanted, from a function generator. But in this case, we're just going to use a slow timer just to create a toggling input, right? And we're just going to say basically 1 toggle per second, like flipping a switch on and then off, every second or so. So we know how to do that. Timer 7 we're going to use as in the same fashion, but just to control the rate of printing values to the console. If we, printf takes a lot of cycles, so if we have too many of these printfs, it can really slow down the microcontroller. So basically, we don't want to print the value of y of t at every time we update those state variables, because that's going to slow things down. So that's something we kind of have to be careful with. So in this case, I'm just going to say we're going to print the value of the speed or RPM at 10 milliseconds. Okay, so about 100 times per second. And then timer 10 is going to be a faster timer, and that's going to be going to control the delta t for this simulation. It's going to control the basic time base, so nothing will be happening faster than this timer 10 speed. So I'm going to set that to 1 millisecond, or about 1,000 times per second. Okay, and then we'll set USART to print y of t, right? The value that we're actually calculating for the RPM. Okay, so hopefully that makes good sense. We'll have a fast time, basically be updating the value of our state variables 1,000 times per second. Then every 10 times that we do that, we'll go ahead and print the value of y, the output. And then of course this input is just going to be toggling, just so we can kind of see a constant response to a changing input. Okay, so that's really the strategy for how we're going to implement this in the embedded controller. And down here I basically just remind you to be careful with printf. If you printf everything as fast as it's happening, you run the risk of really bogging down the simulation and having some of these interrupts stepping over each other and maybe not finishing a calculation before the next interrupt is triggered. So that's going to be kind of outside the scope of this class, but just know that sometimes if you have a lot of things happening in a callback function, you want to make sure that the period of that callback function is long enough to be able to do all those calculations, or else they'll start running into each other. Okay, so this is really how we're going to implement that, and we'll go through an example of this, so you'll see how this works. But here, we're using this, we're basically using 3 timers with 3 different periods, and implementing those inside this period elapsed callback function. So this callback function will be issued every time one of these timers, triggers an interrupt. So for timer 10, we're doing this very quickly. This is the 1 kilohertz timer where we're actually updating our state variables. So you can see we're updating x1 based on a previous value of x1 plus our delt, which is our delta t, times x2 old, right? So we have our new state variables in terms of our integral estimation, right, of our derivatives times delta t plus our old value, which is given in terms of our transfer function parameters. So this, is just another way of implementing what we just said above in these equations right here, right? x1 is x1 old plus delta t times x2 old. So really we're calculating new values of the state variables, and then after we do that, we're assigning x1 and x2 old are now equal to those. For the next iteration, we'll have a new delta t, or we'll have the same delta t, but we'll have new values of this x1 and x2 old, and maybe a new value of the input u old, and then we can basically iteratively calculate our state variables each time this callback function happens, which is at a 1 kilohertz rate. Okay. Also, we'll have our timer 6, which is our 1 hertz timer. So that's just simply going to toggle this u value between 1 and 0 every time this callback function is issued for timer 6. And every time it's issued for timer 7, we're just going to use that at a 100 hertz rate to print um, this basically our RPM value. Now you'll see a weird format here. Normally we wouldn't have this $ or this semicolon, but I'm using a open source program that will basically plot from values coming out of the serial UART. So that's a real convenient way to just show things on a screen without having to, look at a scope or, physically output a signal, to a GPIO line to go into a scope. If you're at home, you can actually just run this program. It'll monitor your UART, and if you're sending values out in time, it'll actually plot those values in time. So it's a really convenient program for that. So anyway, that program requires, basically a $ at the beginning of the data and a semicolon at the end of the data. You can have multiple values. If you want to plot multiple channels of data, you can separate those values, by a space or a comma. But, for each time iteration, you want to start with a $ and then have a semicolon, okay? And then the next time you have a $ and semicolon, it's going to count that data as, another point in time, if you will. Okay, so this is really the meat of our control system simulation, right? Other than maybe, defining these, we have some variables up here that we need to define up above. We need to set up these timers. Other than that, this is pretty much the meat of how this thing is going to be implemented. Okay, and if you run this, using this serial port plotter program, and here's a link to that if you want to install that. I found it to be pretty easy to use. It's a little weird, the user interface. We'll go through and kind of play with it a little bit here when we do an example. But, for example values that I chose for omega sub n and zeta for that control system, you can see what's actually plotted here. So down here in the box, this is data that's being spit out of our UART from our embedded code, right? And this is basically just picking those up and plotting those over time. Okay, so you can do some scaling. You can have multiple channels. If we wanted to plot the derivative, we could, our x2 variable. But this is just basically plotting our x1 variable, which is, coming from this printf statement. So you could do multiple channels if you want, more fidelity and print more information. You could. This thing will plot, multiple channels, and that would look like, space separated values horizontally for each one of these printfs. It would interpret that each one of those as a different channel. It would plot them up here, channel 0, 1, 2, 3, 4, and so on, like as different colors. So it's good for that. Okay, so we'll go through this example after this lecture video on these slides, and I'll show you how to code that up. And then what I want you to do is to kind of repeat that, but for just the motor and driver. So once you derive the parameters for the motor and driver, that K sub G and T sub M, I want you to basically implement that dynamic system in the microcontroller and look at what the response of that system is. And it should look very similar to what we measured before, right? We go back up. It should look like this. Of course, in simulation, it's going to be a little bit cleaner than in this real world data capture, but you'd expect, to see this first order response for the simulation of that first order system. Okay. So basically we'll use this transfer function. In this case, we use the same setup for simulation, 3 timers, right? We use timer 6, 7, and 10, right? So really the only thing you'll need to be changing is the state space representation of now the first order system. Okay, so you need to form the state space equations for that model and basically implement that in the code. And then you can use your serial data plotter, this guy up here that I've sent a link to, and basically provide this plot. Okay, so one difference is for a state space, for first order system, we only have one state space variable, so the equation gets pretty simple, right? Really, we have our state space one variable, x of t. We don't have x1 and x2 anymore. We have one state space variable, and that's going to equal the output. So we can write our one dynamic equation as y dot is going to be kg over tm times u. So if you take this and multiply it out and take the inverse Laplace, you'll get this kg over tm times u minus 1 over tm times x. Okay, and then we're basically estimating y of t by taking the integral of this y dot. Okay, so that's going to be the estimation of the integral is the previous value of x plus delta t times x dot, which is y dot, right? Okay, so in this case we don't have x1 and x2 and x1 old and x2 old. We really just have, calculating our y, and that's going to be based on y, which is our x, and that's going to be based on x old. Okay, so you should be able to modify the code from the example we're about to show pretty easily. Instead of having 2 state variables, now we just have 1, and then it's pretty easy to calculate that output. When you do that, you should see something that looks like this. So this is what we would expect from a first order system response, right? So if you were to change the time value, that's going to change this time constant. If you were to change kg, that would kind of change this final value, if you will. But it should look something similar to this, right? This is a first order response we would expect. Okay, so now let's go through and actually code up that programming example. I'll show you how to use the serial plotter, and we'll basically reproduce the example we just kind of showed in the slides. Okay, so let's start a new project. Select our board. Okay, I'm going to just call this second order sim example, something like that. I'm going to go ahead and use all this default. No here is almost always the right thing to use. Okay, once this opens up, first thing, since we're using a lot of timers here, let's look at our clock, make sure that's set, and that's going to help us determine our parameters for the timers. So let's go to clock config, and you can see APB1 is going to be 12.5 megahertz. APB2 is also APB2 timer is 25 megahertz. So let's look and see. We're talking about using timers 6, 7, and 10, right? So let's look and see what buses those are on, just to make sure, because that's going to impact our time settings, right? So let's look at the reference manual, make sure we know what buses those are going to be on. Okay, looking at our reference manual, let's go to memory map, and let's go down to our timers. Okay, so APB1 is everything, I think, but timer 1 and 8, right? So APB1 is the bus for timer 6, 7, and where's timer 10? Nope. Timer 10 is on APB2. Okay, so we need to account for that in our programming, because we know that APB2 is going to have twice as fast of a clock rate as the other timers on APB1, right? Okay, so for timer 10, we have 25 megahertz clock bus, and for the others we have 12 and a half. Okay, So remember, for timer 10, we wanted it to be the fast rate. We wanted that to be basically 1 millisecond update event rate, right? Okay, so let's enable our timers and get those configured correctly. Okay, so we want a timer 6. And all these are going to be in interrupt mode, right? So we're going to need to make sure to enable the interrupt because we're going to be, taking action on the callback function for these. Okay, so 12.5 megahertz is the clock bus for this timer, right? And we wanted to do this every second, right? So let's just kind of make this easy, and let's just divide it down to about 10,000 counts, and then we can. That's a reasonable number. That's within the 16-bit number. So if we divide that by like 1250, that's going to give us 10,000 clock cycles per count, right? So if we want to do 1 second, it would be 10,000 counts, or 9999 counts would give us a period of 1 second, if that makes sense. Okay, so basically 100 microseconds per counter cycle, or per counter count. So if we make this 1249, then this, every 10,000 of these will be 1 second of period. So since we want this to be timer 6 is controlling the toggle every second, we want this to be 10,000 counts, or 9999. Okay. So now we want timer 7. That's going to be how often we're printing, which is going to be basically 10 times a second, right? Or no, 100 times a second. So 100 times as fast as this. So if we activate this, go ahead and set this interrupt before we forget. 1249. So 10,000 cycles per second for the count, and we want to do 100. So this will be now 99, right? So we can check our math and say, so each count will have, if we do 1 over, that's going to be basically 0.1 milliseconds. And we want this to be 100 milliseconds, right? So we want this to be 100 hertz, or 10 milliseconds each, and then 1 over that. So 100 counts. Yep. So 100 counts. So basically a factor of 100 from our simulation. Actually, we want it to be a factor of 10 off our simulation, right? So if our simulation was at 1 kilohertz, we want this to be at 100 hertz, which means we want clock cycles to be 10,000 divided by 100 was 100. Okay, I think that's correct. Yeah. So for the so we want to be 100, factor of 100 from our 1 second toggling, right? Which is at 9999. So if that makes sense. Okay, now for timer 10, again, we're going to enable the interrupt for this. And now, remember, this one's on a different bus. It's on a 25 megahertz bus. So let's divide this by 2499. That's going to give us 25 million divided by 2500, which gives us 10,000. And we want it to be every millisecond, right? So this will be a factor of, let's see, so we want basically every 10 cycles will give us 1 millisecond, right? If every one of these cycles is at 0.1 millisecond. So that would make this one 9. Okay, so you can play with different prescalers, different period values. It's up to you how you want to decide, but the key is to pick prescaler values that give you reasonable periods that are within the limits of the timer. So the prescaler is limited here by 16 bits, You know, this may be a 16-bit or a 32-bit timer, so the period in this case is limited to 16 bits. So, you know, you want to make sure that you pick values where both of these can be within, you know, 65,000. That's, you know, in this case. Okay, so there's our timers set up. Let's turn on our UART. Use UART2, asynchronous mode. Here we don't need to use interrupts or anything. We're just going to be using that printf function, right? Okay, so I think everything looks good. Let's generate code. Okay. All right, so we should have this thing configuring our 3 timers and our UART. So let's see, what are we going to need to do here? We're going to need to create some variables, right, to describe our second order system. So let's create those up here in global space. We'll say float. So we need to create variables that's going to keep track of our input, our old value of our input, our state variable values, the old values of our state variables, and then the parameters of our control system. So we'll use U as the input. U old will be the previous input. Then we need x1 will be one state variable, x1 old will be its previous value, x2 old, and then we have the parameters of our system, which we're going to call omega sub n for our second order system. Remember, we have omega sub n and zeta, right? So let's just do that. Okay, so we've got our I think that's all the variables we should need for this. We do all the configuration. Now we need to basically assign values to these. So let's say, as an example, we use omega sub n is 2 times pi times 20. So let's say omega sub n is basically 2 times pi times 20. Zeta, let's use a value of 0.2 just as an example. And our delta t, since we configured the timer, we know what that'll be, right? We set the timer 10 to be at 1 kilohertz, so we know delta t is going to be 1 millisecond. So we can go ahead and set that delta t value. Okay, so again, just as an example, whatever these values you want to simulate, we can do that. Okay, now we need to actually, timers are all configured, right, up here automatically, but we need to actually start them. So we need to go down here to user code section 2, how timer base. So we're all using these just kind of in basic mode, right? We're just basically starting the general timer in IT mode, right, for interrupts. And we'll do that for all of these. Timer 6. And we'll do timer 7 and timer 10. Okay, so we've started all those timers. Then this basically is just going to go, you know, in an infinite while loop, and really all the action that's going to happen is going to be triggered by these interrupts, right? So when an interrupt for 6 happens, we'll toggle the input signal. When an interrupt for 7 happens, we'll print the current value of the state variable, notably the x1 variable, specifically that one. And for timer 10, when that interrupt happens, remember, we'll be updating our state variables. That's the simulation rate, if you will. Okay. Okay, so all these should be configured. So let's go down. Before we forget, let's go ahead and put in our put care code so that we can print f to the console. So I'm going to put that in basically down here in user code 4. Okay, so I just copied that from a previous project. Remember, this is so we can use printf and output that to the console. That's going to require us to include standard IO .h. Okay, and it's also going to require, once we do printf, that we enable that weird checkbox for using printf with float. So we'll need to eventually deal with that. Okay, so we need to implement our callback function. So all of these three timers are going to be issuing the same callback function, right? So these interrupts, they all have different interrupts, but the invic is going to basically, let's see if we go to the it.c file, we should see that, you know, we have IRQ handlers for all three timers, 10, 6, and 7. So timer 1 up, timer 10 IQ handler, timer 6 DAC IRQ handler, and timer 7 IRQ handler. So these are the three separate invic interrupts that are going to happen with those three timers. Each one of them is calling the driver IRQ handler, right, and sending it the particular timer, and then the driver is going to interpret what action caused the interrupt, and it's going to send you that callback function along with the timer that caused that specific event to happen. So all that luckily is configured for us automatically. We just need to have the callback function that will you know, parse out the timer that sent the callback and then take the appropriate action. Okay. So if we want to find the callback function, the best way is to just go into the driver for the timer and pull that out. So the APIs are listed first. Scroll down a little bit more, you'll find the callback functions. We want our regular just period elapsed callback. So I'm going to Control F and find that actual function. Okay, it's right here, the weak implementation. So I'm going to make a strong implementation of that in my code. So I'm just going to copy that whole thing. Don't try to type it out. You'll almost always have an error. So I have that. Okay. So now we want to have the three cases depending on which timer it is. So let's start with the slowest one. If each time, so if this is callback, it has been called because of timer 6. So H timer is basically the handle of the timer that caused this callback. So I'm going to say if that handle is the same as basically H timer 6, if they have the same address. You know, there's different ways to do that. We've talked about that, but this is how I'm going to do it. Then basically I'm going to use this to toggle U, right? So there's different ways to do that. You could XOR U with itself. U equals, you know, XOR of U. You know, I think in the example, if U is equal to 0.0, then now I'm going to say U is equal to 1.0. And then else U equals 0.0. So if it's equal to 1, we'll make it 0. If it's 0, we'll make it to 1. Again, this is going to be at the rate of once per second. Okay. All right, so that takes care of toggling the input. Okay. Toggle system input. Okay. Then we'll have H timer 7, which is the printf, right? So if H time equals the address of H time 7, then we will use this to print the state variable associated with RPM, or the output of the system, Y, right, is going to be X1. So if that's the case, we're going to printf. In this case, remember, since we're using that serial plotter, the first character in each line needs to be a $sign. Then we can say percent 0.5 F, so a 5-digit, 5-decimal float, and then we need to end with a semicolon. You know, maybe for grins we'll change this in a little bit to print two different state variables, and then we need to have you know, \r and n to make sure that goes to a new line, and then we're going to print x1. Okay, so you see we get our little error because we're using printf with float. So we need to go to our project. See if I can find it. Sometimes I have to dig through a little bit. There we go. Takes me a little time. Usually end up getting it though. So here we're going to use float with printf. It's going to get rid of that error. Okay. All right. So now we need to actually implement the code that's going to update the state variables at the 1 kilohertz rate for timer 10, right? So if htimer equals the address of htimer 10, then we're going to basically calculate our new state variables based on previous state variables. Okay, so in this case we have x1 is going to be equal to the previous value of x1 plus our time delta, our delta t, times our x2 value, right? Old x2 value. Because that's going to be x2 old is y dot, or x1 dot. So x1 old plus delta t times x1 dot, that'll update x1. Okay, and then for x2 we can do the same thing, x2 old plus delta t times, and now we have y double dot, remember, which is going to be related to our second order response of our system. So minus omega n squared times x1 old minus 2 times zeta times omega n times x2 old, okay, and then plus omega n squared times our previous input value. Okay, so again, just from the slides, this is how we simulated our second order system. Now we need to update our old values. x1 old is now equal to x1, x2 old is now equal to x2, and u old is now equal to u. Okay, so u is changing, but really we're only using the previous value of u in these equations, right? Okay, so we don't initialize some of these values, x1 old and x2 old and u old, so let's go ahead and make those initialized up here. Let's go into our main, and let's say before we go into our infinite loop, let's just say x1 old equals 0, x2 old equals 0, and u old equals 0. Okay, just initialize those to 0. Okay, now we're updating these. Okay, so I think that's all we need to do. So at 1 kilohertz, we'll be updating all our state variables continually based on the input. The input will be changing here every second if we got our timer configured correctly, and then we'll be printing basically 100 times a second. Okay, so let's build and see how this looks. Okay, got some errors, that's good. Okay, it doesn't like delta t, so I think we forgot to, oh, we have this here. Oh, we didn't actually put that up here in our private variables, so add delta t to that. Okay, so that's a float. Okay, 0 errors, so that's good. Okay, so let's run this, and then we'll open up the serial plotter. So go to that link I gave you and install that, or just, I think there's actually an executable you can download. It's like a Win32 type application or something, but I think they also have the source code. If you want to actually compile it for whatever system you're on, you can do that as well. Okay, so this thing should be running. If we were to open up just our serial console, you see here we're spitting out our values. You can kind of see it's toggling from 0 to 1 with some oscillations and things. See our $sign and our semicolon are there, so our serial plotter should be able to basically use those as delimiters to grab those values. And we're on COM4. Okay, so let's pull up our serial plotter. So when you run that, it looks like this. Just a quick orientation. At the top, there's a play button, pause and stop. So the stop will disconnect the COM. Play will start connecting to it. Pause, you can pause it if you want to pause the plot if it's changing quickly. This button right here is basically to record the data or not. So right now, if you toggle this, now it's going to record everything that comes through this into a CSV file. So you'll see a message down here in the bottom left when you toggle that. It's kind of not obvious which state it's in, right? But if you click it, you see at the bottom, data will not be stored anymore down here. If you click it on and it's visible, and it'll say data will be stored. So if you have this on, you can actually store this data into a CSV file. And you can read it into Excel or anything else, MATLAB or something. If you wanted to take a waveform and take the FFT or something, you could record it and throw it into MATLAB or something like that. Okay, so right now we're not going to record. So COM4 looks like it should be correct. So let's go ahead and hit play. And you can basically see the UART values are screaming through here, 100 per second. And you can see this thing plotting. It's picking up one channel because there's only one column of data here. So it's convenient to use this auto scale axis. So the first time you press it, it doesn't seem to fully auto scale it. Kind of goes from 0 to 1, and then you can press it again, and then it'll kind of adjust accordingly. So I don't know why. Sometimes you have to press that a couple times, but here you can basically see this is the response of our second order system. So this is kind of what you'd expect, right? It's toggling about every second, right? Our input signal is toggling every second. And we have a real high ring, right? This is a very, lot of overshoot, a lot of oscillation. So you can imagine that the locations of our roots are going to be, such that it's changing very fast. So that those roots are going to be, far from the origin, but also, kind of close to the vertical axis, right? First, close to that J omega axis in the S plane, because that our sigma is negative, but maybe not very negative because there's a lot of oscillation. So we could go in and play with the values of omega n and zeta, and that would change this response. So just as an example, let's go do that. Let's say we want to make omega n less. So let's make this 5. Keep zeta the same. So changing omega n is the magnitude of the pole location, right? So I would expect things to, the system should move slower or have a different oscillation, right? Okay, so now if you go back to our response, now you can see, I'll maximize that. Now you can see a much slower oscillation, right? So before we had a faster oscillation. So in this case, the magnitude of omega sub n is going to control the frequency of your oscillation, right? Remember in the performance control system performance lecture, we saw how the magnitude of the location of those poles kind of was related to your frequency of oscillation. That zeta was going to be, and omega n together, were going to be related to how fast this thing actually, converges. So here you can see the time constant is very large. It's taking a long time to settle down. So let's just to play with it, we can go in and let's change zeta to something, let's see, let's make it, what was it? I just erased it. It was 0.2. Let's change it to 0.01 just as an example. That might not look very good. Let's see what it does. So yeah, this is looking pretty nasty, right? So basically we shortened, yeah, so interesting, right? It's actually unstable now. So we must have gone into a realm where we have roots in the right half plane. So this thing's going to continue to grow until we reach the limit of the float, right? So unstable. So let's go back and let's change this to maybe, let's change it to 1. That should help move the poles further to the left, which gives them a more negative sigma value, which means there'll be much faster decay to our system. Okay, we gotta wait till this old values clear off so we can rescale this thing. Okay. It's not scaling very well. So let's, maybe we can change it from 0 to 1. All right. Okay. So now you can see we must have actual real roots that are not complex conjugates. So we basically have no oscillation. The thing is overdamped. That means the roots are real and on the sigma axis. So it's like a double root, right, on the real axis. And we have no oscillation, definitely stable. So we've kind of changed our, the quantity and the radical for those roots is now a real number. Okay, so anyway, the point is, this is plotting the response of this second order system, right? So we can change those system values to whatever we want, omega sub n and zeta, and it's going to actually give us the step response, right? So if we were to go in now and change that omega sub n, it wouldn't change the dampedness of it necessarily, but it would, change the response time. But anyway, you get the idea. So feel free to use this program. I think I requested that you use this to kind of show the response. Another option is if you can't get this to work or you don't want to use this, you can just record data straight from your serial connection, from Smarty or some other serial connection. You can just pull data off of that and throw it in Excel or MATLAB if you want to actually plot it another way. But I find this a real nice way to plot, use printf to show whatever these variables are. So in this case, let's go back in and plot x2, which will be the derivative of this, right? It'll be the y double dot, or it'd be the y dot. We can show that as a separate channel. So if we go in here and printf another float, and we'll make that x2. Of course, we've got to keep our $sign and our semicolon as delimiters on that data. That means the serial plotter program is going to basically think that this is now 2 channels of data. So now you can see there's 2 channels. I'm going to stop this and reconnect it. I'm not sure why it's not plotting. Oh, I think it's because these values are not current. At some point I think you fill up the window here, so it's not really real time showing these values, which we don't really care that much about, right? Okay, So let's auto scale. Oh, that didn't work very well. Let's make this minimum -5, maximum of 5. So here you can see that red is our actual output. Yellow is going to be the derivative of our output. So you can see whenever that step function hits, obviously that derivative is going to go really high, right? So we could maybe make this -10 to 10. But here you can see, we have a step function in the input. So our output is going to have a very high derivative in the beginning. Then that derivative is going to kind of decay to 0 as this thing settles out. So you can see the actual value of our y dot is actually getting to be some pretty large values. I'm not sure how. There we go. If we go to 100, we can kind of see the limits of it there. Yeah, so it's I don't know, maybe like -15 to 15. There we go. So so you can use that to plot your various values. If you wanted to plot u with this, just to see where that is, you could also add that. Plot u, right? Add a third channel if we wanted. Okay, so now we have channel 2, which is, you can kind of see it on top of there, right? So now you can see the actual toggling of the input. You can see that, the y dot kind of coinciding with our input step function, which is what you'd expect, right? So anyway, there's an example of how to implement a second order control system in an embedded system, or second order response, simulate the second order response of a system in our embedded microcontroller, and using this serial port plotter application, which I think is a really good, easy way to just pull data out of the microcontroller using printf, not having to use a scope. Pretty reliable way to plot real-time data. Okay, so basically, when you do the assignment for simulating the response of the motor and driver, obviously it's going to be pretty straightforward. It's just going to require a modification of this code, right? So essentially now we're only going to have one state variable. So instead of x1 and x2, we'll just have x. We'll have one state space equation, and of course the parameters of our system here are going to be different, right? It's going to be in terms of kg and tm. So, you go through the slides. It should be pretty obvious how to modify this section to use the values that you derived, as well as for a first order system. Everything else should be pretty much the same. And then I just want you to, submit the source code for that, as well as the, a plot of this or some other program showing that actual real-time response. Okay, so hopefully that helps. We'll be kind of building on this. The final project will be simulating the motor and driver, which is a first order system, being controlled by some kind of controller. So we may have a multi-order system for our closed loop transfer function. By the time we add maybe a PID controller or something like that, I don't think we'll get much higher than a second order system. I could be incorrect, but I think if our PID controller, is proportional control, or integral and differential, so we're really only adding one more degree of differentiation on top of our first order motor and driver. So I think that would equal maybe a second order system. Maybe it's third order, but anyway, the concept is pretty much going to be the same. It's just really how do you define these integral estimations of your state space variables. So it's not too difficult. And again here, the key is having a consistent delta t and a consistent time base for calculating all this. So if you somehow have this this timer 10 is inconsistently executing, then you would actually need to maybe have some other corrections in here to calculate the time delta and then use that in these equations. But once you start having a variable delta t you really start getting into kind of dangerous territory of having some errors, because if that delta t is changing quite a bit, now this integration estimate is going to be off, right? Because these values may not be associated with the correct delta t. So really you want to make sure that whatever you're doing in this callback function, it can be executed in the amount of time between callbacks. So in other words, this code needs to be able to execute in 1 millisecond. And you know, you could print out the time it takes to do that if you wanted. You could grab, you know, the ARR, not the ARR, but you could grab the current count value from timer 10, you know, here at the beginning and here at the end, and kind of look and see how many actual counts out of that period, you know, out of the I think this one had, you know, 9 counts per period. You can see how many counts this is actually taking, to see kind of how close you are to that limit. So if you have a lot of state variables, you know, you may have to increase your delta t a little bit so that you can actually do all the calculations in one cycle. Okay, so we can next time we're in class, we can talk about this if you want. But I'll post the assignment very soon for the simulation of the first order motor and driver, which is just a quick adaptation of this. Okay.